Alright guys, welcome back. We're going to continue our talk on semiconductor physics. We're going to talk today a little bit about metal semiconductor junctions. There's two types of these junctions. There's the Schottky diode and the Ohmic contact, and really physically what's different about them is that we change usually is doping. But the Schottky diode, which is the first diode, one of the first electrical diodes ever made, is a rectifying device. And Ohmic contacts are just a metal semiconductor junction in which current can pass both ways unimpeded. And so we'll start our talk with just defining some stuff here. So we got our vacuum level. We have distance here, which is the work function of the metal, energy in which energy needed to take an electron from the metal and then accelerate it out to infinity, so it can't go back. And then over on the other side we have the semiconductor. We'll use an N-type semiconductor for reference here. So this is a donor doped semiconductor with our semiconductor electron affinity here and our semiconductor work function here. So what happens when we bring these two together? What happens when we deposit some metal on a semiconductor, say silicon for this case, donor doped silicon? Well, let's bring these closer together and see what happens. So given that the work function of the metal is greater than the work function of the semiconductor, right, then what happens at the surface, I'm just going to line up our Fermi levels. What happens? So that means the distance here is greater and the distance here comes down like this, right? So what happens is we get this bending right here in the semiconductor at the surface. So electrons from the semiconductor kind of get sucked into the metal, and it pulls the Fermi level of the semiconductor down at the interface. Right? So the interface will be slightly less N-type than in the semiconductor bulk. There's our EI, EV, conduction band, EF Fermi level, and E conduction band. So there it is right there. So what happens when we apply some voltage to this, right? Let's say we apply a forward bias, right? Forward bias would be VA greater than 0. So that would be the positive electrode of the battery here, negative side of the battery here, right? Well, so what's going to happen is the Fermi level in the semiconductor will be, on this side, will be pushed up in reference with respect to the metal Fermi level of the metal, or the affinity, right? So we see here that there's this new barrier, there's this new potential difference between the two quasi-Fermi levels, and that's going to be our V applied, right? And then now our potential across the semiconductor is our built-in potential minus our applied voltage, just like that. And another thing is what kind of current is occurring in a metal semiconductor contact, right? Well, let's go back to our equilibrium model. So if you remember from before, if you were to plot energy as a function of your carrier density, electron density, it looks something like this, right? There's a conduction band, valence band. This is energy, and then if we plot N, which is the integral of our Fermi function times density of states, that's F times G dE, right? We get something that looks like this, right? Just like that, right? And so if we were to stick the same plot and superimpose it right here, looks like this, right? So the electron density in this region right here it is blocked by this barrier, so it can't pass. However, when we apply a positive bias, we push this up, right, and we lower the barrier right there. We get something like this. Now, without that barrier there, and with a supplied electric field, carriers will pass through the metal semiconductor junction unimpeded. This is called thermionic emission current. There's a derivation for it to get the diode equation for metal semiconductor contact, or a Schottky diode. It's a pretty long derivation. If you wanted me specifically to do it, you just write it in the comments, and I can derive that in probably like 30-40 minutes. So same thing though, if we apply a negative bias, you know, negative terminal here, positive terminal here, semiconductor Fermi level is pulled down here with this positive side right here, and now we really don't have any thermionic emission current, right? None of it can pass, right? So that's what makes this a rectified device. Similarly, with an ohmic contact, we'll show that through the derivation, we'll show that with high doping, the depletion width will get so small that this distance right here will be so thin, electrons can just tunnel right through. And you can derive that from the transmission, we call it transmission current or tunneling current. It's a concept in quantum mechanics. So I can go over that later if you guys want. So I'm going to put that in comments. So let's just define everything out here before we start deriving. Here's our metal semiconductor junction. We have put our x-axis here. X equals 0 is our is the actual the interface between the metal and the semiconductor, and then x equals w is the length of depletion width. After x equals w, the energy bands flatten out, our electric field goes to 0, and we're in the semiconductor ball, right? Another important thing is this distance right here. You know, from the metal Fermi level up to the top of this conduction band of the semiconductor, and that is our barrier height, or Schottky barrier height, right? Just like that. And you'll see the Schottky barrier height comes from E. It's simply the charge E times psi m minus chi s. So metal work function minus the semiconductor electron affinity, right? And then similarly, we also have a built-in potential across the semiconductor going from the interface into the bulk, just like that, right? So at x equals w, the potential is the built-in potential. At x equals 0, the potential is 0. So let's take a look at the Poisson equation. Right. We have, let's erase this for now. Maximize our real estate here, so we're gonna need a little bit. So d squared psi of x over dx squared equals negative d electric field of x over dx, which is equal to negative electron or charge density, positive charges, sum of the difference of positive charges and negative charges in the semiconductor over the permittivity of the semiconductor, the silicon, right? And so in this case, we know rho is equal to charge, electron charge, times positive charges minus negative charges. So looking in the depletion region of the semiconductor, right? The term that dominates the most is ND, right? Yes, there's some N, there's some P. It's very small, but in general we call it the depletion region because there are no free carriers in that region. And it's not, there's no acceptors ions because it's not acceptor doped, it's donor doped. So we can get rid of all this, and we can rewrite this equation just looking at dE. dE of x over dx equals E ND over ESI. Okay, so let's make some boundary conditions real quick before we go on here. So at x equals w, our electric field is 0, correct? And x equals w, also our potential is our built-in potential. And x equals 0, our potential is 0. Okay. So we're going to integrate both sides. Bring dx over here. Integrate both sides. We get E and D over E silicon x plus C. Right? Let's apply boundary conditions. What is E at W? Well, that's equal to 0. So it's equal to E and D W over E silicon, right? Plus C. So C is the negative of that, so we can rewrite the equation. E of x is equal to E and D over E silicon x minus W. Right? Okay, now we integrate again. This is also equal to negative d psi over dx, correct? Right? Psi is a function of x. So we bring x over here, we integrate both sides, right? And what we get is psi of x is equal to E and D over E silicon x w minus 1/2 x squared plus c prime, some constant c prime. Apply another boundary condition. Psi of w equals psi bi, our built-in potential, which we don't know yet, which is equal to E and D over E silicon. So that's w squared minus 1/2 w squared, so that's going to be 1/2 w squared plus c prime. So what does that tell us? That tells us c prime is our built-in potential minus this term right here. Okay, so ran out of room, so we're going to go back to the top. And now we have our potential as a function of x. Our potential across the semiconductor, going from x equals 0 to w, we get this equation right here. E times our doping over 2 times permittivity of the silicon is, so it would be 1/2 x squared. Let me think here. Make sure that's right. I think I erased a little bit too much too fast. Yes, okay. Plus minus, backtrack here just a second. What do we have before? We had psi of x equals E n d over E silicon wx minus 1/2 x squared plus c, which is psi bi minus E n d over E silicon 2 silicon w squared. So our psi of x is equal to E n d over E silicon wx minus 1/2 x squared minus 1/2, so my handwriting, w squared, all right, plus psi bi, right? So our potential in the semiconductor is your psi bi plus this function of x right here, right? And we know that psi is related to energy by this, or our potential is related to the energy is this 1 over E times E, negative, right? So if we were to plot psi, it would look something like this, right? That's x, and this is psi of x, right? Well, what if we flipped it? We normalize our conduction band, our valence band at the bulk to be 0, and we basically just plugged the negative of this into MATLAB, and we would get a curve like this, right? Just like that, right? And then similarly, we could add the band gap to this So this term plus the negative of this term plus the band gap, and we get a curve like that. There's our valence band, and then we figure out and halfway up is our intrinsic Fermi level, like that, and then we could just plot the Fermi level in relation to that. So you could plot this as a function of that. Plot your potential or your energy band diagram as a function of x in MATLAB. So next step is we want to derive a term for the depletion width. This W right here. Okay, so we know that psi of W minus psi of 0 is equal to psi vi, correct? And so these two terms, so this term minus this term is going to give us E md over E silicon. E of W is 0 because this squared minus this, plugging in W for x is going to be 0, so it's 0 minus psi is 0, which is 0 minus 0 minus 1 half W squared, so that becomes a plus 1 half W squared. And then it's psi di minus psi di, which is 0. And we find that our built-in potential is equal to E md over 2E si W squared. And so that means that if we solve for our depletion with W, we get 2E silicon over E md psi vi, right? And just as with a PN junction, when we implement a applied voltage, we can change this equation to just W of V applied, which is equal to 2E silicon over E md psi vi minus V applied, right there. So that's our equation for our depletion width. Okay. So what does this tell us here? So this tells us the depletion width is dependent on doping and dependent on applied voltage. So leaving aside applied voltage, let's say we have really, really high doping. Let's say our ND is approximately NC, our total effective density of states in the conduction band. Well then, we're going to have something like this. Oops. Just to give you a better picture, to our Fermi level all across, be something like this. Right? That's what we do. Right? Our conduction band and our Fermi level are approximately equal right here. And obviously that can't happen in real life, but we can get it pretty close, even with non-degenerate doping. So we get it really close to the conduction band like that, and our W here, which is a function of doping, is now very, very small. So that means if there's, now with the barrier, our barrier is still here, right? And our electron lie in this region right here. However, because this barrier is so small, electrons can simply tunnel right through very easily, right? And this is based off of tunneling coefficient. And I can always derive that in another lecture if you guys wanted. So, that is tunneling in a metal-semiconductor junction. We went over rectification in a metal-semiconductor junction, which is Schottky diode. So what would be the difference between a Schottky diode and just an ohmic contact? Well, an ohmic contact, which is what this is right here, has high doping, even degenerate doping, where a Schottky diode has smaller doping. For silicon, it's usually on the order of 10 to the 17 or 10 to the 16. Right? Within that range, you can have good rectification without having to worry about tunneling. So, one other thing to kind of discuss about metal-semiconductor contacts, and we probably won't really get into this unless somebody asks about it, is these are based off ideal conditions. In reality, there's a lot of things that are happening in a metal-semiconductor junction, with silicon and metal especially, that aren't really taken into account in these equations. We have something called metal-induced gap states, which actually pin the Fermi level of the semiconductor at a certain level, so the band is already bent before any metal comes in contact with it. And there's kind of a small dielectric type region in between the semiconductor, call it a delta region, because it's like 4 to 5 angstroms, like half a nanometer, right? And the Fermi level is actually pinned at some region, usually about a third of the band gap up, before it even comes into contact with the metal. And when the thing about silicon is it's the pinning is very is not very much, not at all really dependent on the work function of the metal. So the silicon is generally going to have a barrier height that's not only independent of doping, but is independent of whatever metal you kind of use. There are other semiconductors, the zinc oxide, not necessarily gallium arsenide link, but other semiconductors that are highly dependent on the metal work function of whatever metal you're using, but silicon is not really one of them. And obviously this is only half a nanometer, so your carriers can flow through it very easily. But I think a great exercise would be go back and try doing this for a p-type semiconductor and see how hole current actually occurs when you have something like this right here, right? Or this is your junction down here. And given doping for p-type and n-type, our Schottky barrier height, or our band gap, is equal to the sum of the Schottky barrier heights if it were to be an n-type semiconductor plus the Schottky barrier height of a p-type semiconductor. So that's this distance right here plus the Schottky barrier height of the n-type semiconductor. It's always going to be equal to the band gap of some of those two. So that's all we have. If you have any other questions about metal semiconductor contacts, there's a lot that could be talked about. I just think it'd be more important to go into stuff like MOS. So, but obviously, there's for every PN junction, there's probably 2 or 3 of these inside a computer chip. So it's pretty important to understand. So that's it. Thank you.